All right, so today we will talk kind of about some stuff we talked about what feels like about a million years ago, back in, uh, I want to say August, but it was like October, um, having to do with functions and their transformations. So this should be relatively straightforward. I'm going to do a metric ton of examples. Um, the assignment is going to be a PDF, old school. There wasn't a good Delta Math assignment on this. So we're going to do this today and the quiz on, let's see, today's Thursday, so Monday. The quiz will be over complex numbers and completing the square, and it was totally my bad. I meant to do it the other way, but that's my fault. So we're going to go through these. Some of these we talked about, some of these we haven't. So the first one we're looking at right here is going to be the absolute value function. Our parent function is f of x equals the absolute value of x. So if we were looking at it with all the little happy variables, and the function looks like this. F of x is equal to a times the absolute value of x minus h plus k. And my voice is breaking because apparently I'm a teenager. So a is the how like fat the v is, and h and k is the horizontal and vertical shift respectively. So this is one we talked about. I feel like it feels like forever ago. Yes, sir. Thank you. All right, so let's take a look. I mean, I'm just going to fill out this little table on the side here. So absolute value, whatever I put in, essentially comes out negative. So this one's easy. Bing, bang, bong, done. Okay. And if you remember from it feels like a million years ago again, our domain and range, and then in our different forms of interval, inequality, and set. So for this guy, he goes to the left forever, to negative infinity. He goes to the right forever, to negative infinity. I'll do domain and then range. Okay, so that means our inequality will be negative infinity less than x less than infinity. Realistically, if I was going to do this, I would probably just put all real numbers. But if we're going to be fancy pants and say the inequality, this is the way I would do it. And then set notation. And then our inequality. So the one that's weird on this one, can I make this thing bigger? No, I guess I can't. That's a bummer. One that's a little different for this one is going to be the range. So the range has a hard stop at 0, right? It doesn't go below 0. So we're going to have the square bracket for a hard stop that includes 0. And then it goes up to infinity. Cool beans. The inequality for that guy is going to be y is greater than or equal to 0. So our set notation will be mustache bracket y such that y is greater than or equal to 0. A lot of information for one little graph. All right, the next one we're going to talk about is our quadratic. And again, the quadratic is something that you've seen before, so this one should be pretty much review for you. My parent function on this is x squared. And then if you remember when we did completing the square, okay, this transforms into our favorite kind for messing with graphs of quadratics, and that is vertex form. You can do quadratics in standard form, but it is significantly more of a pain in the butt, okay? So I always recommend doing vertex form if you're going to be graphing parabolas, like straight up. So it would look like f of x is equal to a times the quantity, x minus h squared plus k. My favorite form for quadratics. So the a, again, is how fat or how skinny our graph is. The h is the horizontal shift, and the k is the vertical shift. And again, in case you hadn't remembered from before, I always remind myself insiders lie because it moves horizontally kind of the opposite way that you think it would. My vertex is HK. It makes kind of a U shape. Let's see here. So I'm just going to do my table of values. -2 squared would be 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And my graph, by the way, is not the most accurate thing on Earth. But you get the general idea. You can kind of estimate with these things. Somebody's lost and looking for our room. So, to be honest, this should be kind of a steeper parabola. If we're being fancy pants. Wish I could make this bigger on the screen. Kind of bumming me out a little bit. All right. Domain and range, we've done these before, but I'm going to go ahead and fill them out. So a parabola left and right goes on forever. So it's a lot like the last one. X less than infinity. Mustache bracket x such that negative infinity less than x less than infinity. Mustache bracket. And then our range, very similar to our last one. It's going to stop it. It's a hard stop at 0. And then it goes up to infinity. So we have y is greater than or equal to 0. And then y such that y is greater than or equal to 0. For this particular parent function. If we shifted it, things change a little bit. All right, so we've done the two reviewy ones. Let's start talking about ones we haven't reviewed. Now, the pattern here that I'm hoping you're seeing is that the A value does how like wide or skinny the graph is. The H is side to side, and the K is up and down. If you got that, you're in really good shape for this. Because those same principles apply to a bunch of other parent functions. The next parent function we're going to talk about is the square root. And this is a weird looking one, I'm not going to lie to you. All right, the square root one. So the graph of square root looks like this. It looks like we're missing part of it, but that's what it does. When I graph these for what it's worth, I pick points that are perfect squares. If you don't, your life becomes challenging very fast. Because I don't know about you, but I don't know the square root of 2 off the top of my head. I mean, there is one, you can estimate it, but it's much easier to pick the points like 0, 1, 4, 9, 16, so you can get the graph a little bit easier. So our parent function here will be the square root of x. If you remember from Algebra 1, and I'm not going to be a jerk about it, because you might have forgotten by now, you could also write this, by the way, as x to the 1/2 power. Okay? We can do rational exponents. I would not do that in this case, though, because it kind of messes up our transformation function. So here is what we do. This should look a lot like what you've seen before. So to transform one of these guys, it's f of x equals, you guessed it, a times the square root of x minus h. And this square root thing covers all of it, like parentheses, and then plus k. If I wanted to do it with a rational exponent, I'll do it kind of up on the top. That would be a times the quantity x minus h to the 1/2 power plus k. That's acceptable if you're into that kind of thing. I'm not saying you have to. I just want to give you options. Okay, yay. All right, we were on square roots after our outing. Okay. So to me, I'm sorry. The starting point, I wouldn't call it a vertex. It kind of starts at 0, 0 or at HK, depending on if you get um, translated. I call this shape a hill. I don't know like a better word to call it, or like a half parabola kind of thing. Anyway, I call it a hill. Um, when you're graphing these, like I said, it's way easier to do if you pick perfect squares. If you don't, you get weird decimals, and I don't like that. So it should be, and I can't believe I messed up that graph. It should be 0, 0, 1, 1, 4, 2, and 9, 3. That's kind of the default points. Otherwise, you get some nasty decimals, and I'm not about that life. All right, this one has got exciting domains and ranges. So with the square root function, because of the reason of imaginary numbers, right? You can't have the square root of a -1 normally. Our domain has a hard stop at 0, so it goes from 0 to infinity. Our inequality will be that x is greater than or equal to 0. And our fancy pants set notation will be curly bracket x such that x is greater than or equal to 0. And I'm being really thorough with these domain and range things because you never know which particular one your college professor, assuming you want to do all that, is going to pick, and they can be super picky about that, especially if it's Dr. Kruger. Our range on this, we're going to be going positive, so that's a hard stop at 0, and our range goes up to infinity. So our inequality is y is greater than or equal to 0. Our set will be y such that y is greater than or equal to 0. So normally, if you don't do any kind of transformations on this graph, it's only going to stay in the first quadrant. So you don't have any negatives here. You can shift it around and weird stuff happens, but this is normally how it works. Okay, so the next one we're going to talk about has another special kind of thing to it, and it is called an odd function. And we're going to get into even and odd functions later, so don't worry about, freaking out about what's an even function and what's an odd function. I think we're going to talk about even and odds in 2, maybe 3 weeks, so you have an idea. It comes up a bit in pre-cal and calculus. So this one is also probably one you haven't messed with before, and that is the function f of x equals x cubed. I always liked graphing this because I thought it looked like a sideways S. Depending on who you talk to, and I'm going to take a second here because we actually had kind of an argument about this in the math department when we were talking about it. Different people are going to call this different things. What I mean, this point here in the middle, 0, 0, right? Different people call this different things. When I was in school, they called this the point of inflection. So the point of inflection to me, right, is where the graph changes directions. I forget, somebody else called it something else. I think it was called the point of change or something like that. Just a heads up, different people call it different things. I was always taught it was called the point of inflection, though. And I always thought it sounded fancy, so I went with it. Oh, and it says inflection point right there on the thing. The transformation of this one should not be any surprise. It looks just like the other ones. F of x equals a times the quantity, x minus h cubed plus k. And I think by now you're probably seeing the pattern of these parent function transformations. They're multiplied by a, they've got a minus h in the inside, and they got a plus k on the outside. It's actually kind of cool that it always works the same way. So let's do the points. So this is where it gets interesting because you have to keep track of the negatives now. So for the x equals -2, I've got -2 times -2 is +4, and +4 times -2 is going to be -8. -1 times -1 is +1, and +1 times -1 is negative 1. 0 stays where it is. 1 times 1 is 1, times 1 is 1. 2 times 2 is 4, times 2 is 8. So you've got the one side's going to be the positives and the other side's going to be the negatives. It's kind of like a parabola, but one side goes down instead of both sides going up. The intervals for this are nice and convenient for the domain and range, right? Because it goes x to negative infinity, x to positive infinity. That one's easy. Negative infinity, positive infinity. Negative infinity less than x less than infinity. X such that negative infinity less than x less than infinity. Mustache brackets. And the range is going to do pretty much the same thing because it goes up and down. My range is also negative infinity to infinity, written a few different ways. Y such that negative infinity, y infinity. Like I said, you could also say that it's the inequality is just all real numbers. That one's fun. So these are, for the most part, the only graphs that you're generally going to be doing transformations of. Are there others? Abso-stinking-lutely. Of course, this is the fourth and fifth power, like weird stuff like that. They're kind of beyond the scope of what we're doing, so I'm not going to go into all that. And you don't mess with them too much until you get into complex polynomials and pre-cal. So even then, this whole a times the quantity x minus h plus k thing, that does hold. Let's talk about, like, aside from okay, Mr. Clark, I get it, I can fill out some notes, to actually using some of this stuff. So what I'm going to do, and I'm not an English teacher, so I'm not going to be a big jerk about this. I'm sure that normally I should make you write like a complete sentence with proper grammar about all this. You can make a list of bullet points. Like, I'm not going to be upset with you. If I asked you to write sentences, just be prepared. We have a writing assignment coming up in the next couple of weeks, but I don't think this is going to be on it. Anyways, so what we're going to do, let's look at this. Is based on the function, describe the transformation from the parent. So this one only has one transformation, and that is a vertical shift up 5. And if I wanted to be more concise, I could just say shifted up 5. Okay? This doesn't have to be fancy pants. I just want to understand that you know what's going on. Okay, for the next one. This one is shifted to the left. Left 2. This is just like what we did at the beginning of the year. Number 3, we got our parent function. We've only got one thing going on. This guy is shifted right 9. Insider's lie, we're doing the opposite of what that sign is kind of telling us to do. All right, number 10. This one's got a couple of things. 1, 2, 3, 10. 5, 6. How did I do that? Oh, well. All right, so this one's got a couple things going on. The negative means that this is going to be mirrored on the x-axis, right? So flipped on x-axis. So before, this is a gimme. What do you think the 4 is going to do to the graph? Do you think that 4 is going to stretch my graph out and make it, like, taller? Or do you think it's going to squish it and make it kind of fatter? This was the part that when I was a student always confused me, is like, which one does what? So instead of telling you, I'm going to graph it and see what you think. Let's see, y equals negative 4x to the third cubed powers. Oh, Mr. Clark, you wrote down the wrong thing. Way to go. Look at me being a bad teacher. I meant flip on the y-axis. No, let's flip on the x-axis. I'm sorry. I'm blinded today. All right, so as a frame of reference, what I'm going to do is I'm also going to graph the parent function, y equals x cubed. So does this graph look like it's stretched vertically or compressed vertically? Looks like it's a stretch to me because this blue one looks like it goes kind of wider faster. So back in my notes, I'm going to say it's flipped on the x-axis. We flipped it upside down. You also if we want to be precise, it is stretched vertically by 4. It's 4 times as steep. All right, now I have chosen to write number 5 in an extremely obnoxious way that you are not used to. I think some of you can probably see through my ploy. There are 4 things happening to this graph. So the first thing, graph, let's see, open down, it flips over x-axis. The second thing is it is shifted to right 8. Right? It is shifted up 1. All right, so we talked about the 8, the 1, and the negative. What's up with the divided by 2? Divided by 2 was not one of the options we had, right? It was a times the quantity, or a times the absolute value of x minus h plus k. So what's the a value here? I could write this a different way. Like that, and make it a little more obvious. My a is the negative half. So do we think that the negative half is going to be a stretch or a compression? I think it's going to be a compression. So I'm going to pull out my calculator and double check since we're still learning. Let's see here. Let me erase what we had before. Let's see here. So we're getting negative 1/2. Oh, what's mad at me? No, I can't use a calculator. Negative 1/2 times the absolute value of x minus 8. And then we see plus 1. So for reference, again, I'm going to do the absolute value of x. So yes, that is definitely a vertical compression. A vertical compression of 1/2. So there's a lot going on here. So number 1, it opens upside down. Number 2, we shifted it right. Number 3, we shifted it up. And number 4, we vertically compressed it. And we can go back to our notes and write all that down. So this has got a lot going on. And if you can see all of that just by looking at it, you're in really good shape for this. That's really what our goal is here. That's probably the hardest question on here, TBH. Okay, number 6 is a trick question. What is tricky about it? I know that this is down. Parabola, so the U opens down. Is it shifted left and right? There's no H value here. We don't have to deal with left and right. There's only a K value shifted down 4. If you don't have an h, that's totally okay. If it's a 0, we just don't bother with the h part. All right, so we can do it forwards. Now can we do it backwards? What I mean is I can give you an equation and you tell me what it looks like. Can someone tell you what it looks like and you give me an equation? Let's do a couple of those too. Our parent function is the absolute value function, and I want to shift it up 7 and left 3. Do I have an a value I've got to change? No. We can say at y equals, or f of x equals, whichever you like for this one. I need y because it's in the problem. Y equals the absolute value of x. Okay, it says left 3, so I'm going to go plus 3. Insiders lie. And up 7. Easiest 100 you're going to make this year, right? Okay, our parent function for number 2 is the parabola x squared. It is reflected and shifted to the right 9. So if it's reflected, I'm going to start with a negative. To the right means I've got an h. And insiders lie, so we're going to say negative 9. It's not shifted up or down, so I don't have to mess with a k value. All right, let's do one of the new ones, a square root function. All right, it says we're going to go down 4 and right 1. That's not too bad. Y equals square root of x minus 1 for right, and then minus 4. So I haven't done too many roots with you guys. I want to throw in this kind of thing that I do. It's a Mr. Clarkism, okay? When I make a square root symbol, I put this little tail on the end so that I know where it ends. Because it always drove me crazy, like in math books and in my teacher's notes, that I wasn't sure where the square root symbol part ended. So if you see that, that's all it means for me. It's just like it's a mental note, like this is the end of it. It's kind of like if I didn't put the parentheses, I would need to know where it ended. That is totally a Mr. Clarkism. Holy Christmas! Look at number 4. Down to reflects vertical shrink of 1/6. When I do these, and it's got a vertical shrink, so it's going to be a fractional value, right? When I'm doing these, I like to make it the fraction in front. You can do it with the fraction on the bottom thing. It's just mentally, I like to see it as a and then x minus h and then k, because that's how my brain works. But you don't have to do it that way if you don't want to. Times c reflex is going to be vertical strength, so I'm going to do this. There is not a horizontal shift, is there? So we don't have to deal with an h value, so we're just going to put x cubed. And then you've got a vertical shift of down 2. I always double check the ones without horizontal shifts because, like, in my brain, it looks weird to not have the parentheses. But if you don't have a vertical shift, they're not necessary. All right, number 5. Right 6, vertical stretch of 2. I'm going to start with the vertical stretch out front. Have our square root of x minus 6 for right. And I have no vertical shift, so I think that's it. Oh my goodness. Look at number 6. Whew. I'm glad I don't got to graph that. All right, so I'm going to start with my vertical stretch. That's a 1/4. 4/3. 4/3. X, let's see, we're going left 5/3. 5/3. And then up 7/12. He's got a bunch going on. Side note, another side note of Mr. Clarkisms. When I'm writing fractions like this, even when it's really tight on space, I don't do that diagonal fraction bar. And that has to do with when you get into more advanced math courses. If you do that, it's really easy to confuse yourself. So I'm just putting it out there. That's a personal preference of mine. I'm not going to judge you, but I will tell you it'll make your life easier if you don't get in that habit. Let's see. What do we got here? All right, let's keep on a going. We're going to describe the transformations for the given expressions for the parent functions f of x, g of x, or h of x. So we've done it where it was super obvious what was going on. This to me is a little bit more challenging because it's a different format than what you've seen, okay? It's not any different mathematically, but the form is a bit different. So number one, f of x plus 5 minus 3. What do you think that means? Let's say that f of x is x squared, okay? Just I'm going to choose a random parent function. So if we say that f of x equals x squared, when I put f of x plus 5 in the problem, I really get x plus 5 squared minus 3. You see how that worked? So what's the transformation of this function? Left 5, down 3. So when we were talking about these before, remember how it was always a on the outside, h in the parentheses, k on the outside? The parent function is really, it really doesn't matter, which is a weird concept in and of itself. Let's look at number 2 here. I don't care what the parent function actually is. 2 for an a is going to do what? Vertical stretch, right? So vertical stretch of 2. The minus 1 with the x is going to be a shift right 1. And the plus 4 is going to be a vertical shift up 4. So you don't even need to know the parent function to know what the transformation is going to be. So this is the only real change that we had from the beginning of the year, is now I can ask you to do this without giving you necessarily all of the information. Let's think about number 3 here. Our a is negative 1/3, so that's going to be a vertical compression. And it's going to flip it over the x-axis. And the plus 2 with the x means it gets shifted left 2. For number 3, our a is negative 3, so that's going to stretch it 3 and flip it. We don't have anything with the x, so there's no horizontal shift. And the vertical shift is plus 2. Number 5, our a is 1/2, so that's a vertical compression. We're not moving it side to side. We've got a vertical shift of down 9. On number 6, that negative is going to means whatever our function is going to get flipped. And the 6 with the x means we're going to get shifted left 6. So these look weird. I'm not going to lie to you. It looks like they're missing information, but really nothing has changed from what we did before. And what this does for you in the long run is it makes you more flexible in what you can do with the problems. This happens a lot in pre-cal and calculus, where they're asking you to transform something without necessarily knowing what the thing is. Because you can know what the thing is later. It's a very super handy skill to have. Let's see. Did that one. All right, so we're going to do one quick little cheater sheet at the end, and I'm going to let you guys work. And this is legitimately what goes through my mind when I see these. When I see A, okay, my brain goes through the following list. If it's a whole number, that means it's going to be a stretch. If it's a fraction, that means it's going to be a compression. If it's a negative, That means it's going to flip. This is the checklist I go through every time I see one of these. If I've got an H, I know insiders lie. So what that means internally to my brain is that if I've got x minus 8, this is going to be a right shift. If I've got x plus, it's going to be a left. And OK is vertical, that's the easy one. If it's a positive, that's up, and a negative pulls down. So that is my mental checklist. And I think you can see by the way I was explaining it, I go in order of A, then H, then K. I'm very logical sequential. You don't necessarily have to go in that order, but I like left to right. I'm a mathematician. So the work today is going to be on the PDF. There wasn't a good delta math for this that like made sense. There's not a lot of like calculation in this, so it shouldn't be too hard. If you get stuck on one of these ones, notice it's a times f parentheses x minus h plus k. If you get stuck on one of the ones where they don't necessarily give you the parent function, I'm happy to help you on that, okay? I know it's kind of a shift in thinking. But this little cheat sheet right here that I've got on the board, that's what mentally I go through when I'm solving these. So if you do that, honestly, it should be an easy 100.